Seminar of the semester. We'll be off for the summer and then starting up again in the fall. Our first speaker today is Veronica Biffi. She's currently here as a visiting researcher at the CFA, and she'll be here through the end of the summer if you're interested in chatting with her. She got her bachelor's and master's degrees at Bologna University, and then her PhD at LMU University in Munich while also working at NPIA. Her thesis was on the baryonic physics of galaxy clusters from mostly the simulations numerical perspective. She was then a postdoc at NPIA and then at the University of Madrid and then the University of Trieste before coming here this year. So today she's going to be telling us about the velocity structure of X-ray emitting gas in simulations of galaxy cluster mergers.
Thank you. So good morning all. In this talk I will provide some results, describe some results on the project that I've been working on since I joined CFA a few months ago in collaboration with John, and it's, as the title says, mainly about studying the velocity structure of the ICM through X-rays coming from simulations. So briefly, the outline of this talk, I will first introduce a little bit the motivation for this kind of analysis, trying to point out the importance of the synergy between numerical simulations and X-ray observations for this kind of projects. And then I will describe the results about the ICM velocity structure, first from the pure simulation point of view, and then using some mock X-ray data derived from the simulations. And then I will, of course, summarize and conclude. So I think there is no need to explain to this audience why galaxy clusters are important and what they are. So I will just briefly mention that the focus of this study is the ICM, so the intracluster medium, this hot gas that fills the potential well of clusters, tracing the potential well and the total mass of the system, with temperatures that are hot enough to be bright in the X-rays, making clusters very bright extended X-ray sources. The ICM, given its collisional nature, provides us with a lot of information about processes that take place in clusters and drive their formation and evolution, such as it carries imprints about the accretion from the large-scale structure, about merging events with minor, smaller structures or galaxies, and especially about the feedback, which can be energetic and chemical as well. And most of these things can actually be derived from X-ray observations. So the idea behind my work and this project is actually to combine what you can get from simulations with respect to what you can expect from real X-ray observations. And all these processes that I mentioned are actually signatures that motions in the ICM can be significant and can have non-thermal origin. So we usually assume that the intracluster medium to sit in the potential well, sharing the depth, feeling the depth of the potential well, and having some thermal motions essentially, which reflect its temperature. But due to these processes, we expect to find some other kind of motions like rotation, streaming, or turbulence that can be observed indirectly through signatures like, I don't know, the presence of cold fronts or shocks or bubbles in the ICM that can actually induce these kind of motions. And these are very important because in principle, you can use the X-ray observations to derive profiles from the ICM that can be used to infer the total mass of the system once you assume that it sits in a hydrostatic equilibrium within the potential well. And of course, if there are this kind of non-thermal motion, this hypothesis is no more valid. And it's really crucial to constrain the extent of these non-thermal contributions. And of course, with simulations, you can study very well this kind of things because you have full control and full access to the whole time evolution of the system and to the three-dimensionality as a whole. And in fact, like in this recent work from a few years ago, I show an example where you can do something that is impossible or very difficult with real observations, which is really estimating the level of hydrostatic bias in the ICM, looking at the profile of the balance between the gravitational acceleration and the hydrodynamical acceleration on the gas within a simulated cluster. And you can compare this kind of profile, which is a median over a sample of clusters, to the expected mass bias, which relies on different assumptions. For instance, it includes as well the non-thermal pressure support of the gas. And results from this work just showed that, on average, within the boundary of the clusters, the deviation of hydrostatic equilibrium traces quite well the mass bias, and they are both within 10 or 20% level of deviation. So what you can do with real observations, you can either infer constraints on the gas motions in an indirect way, for instance, via X-ray surface brightness fluctuations or pressure fluctuations, but you can also measure velocities, or you could in principle measure directly velocity of the ICM. And the only way to do this directly is actually via the shifting and broadening of emission lines from preferably heavy ions that contribute to the spectrum, since the ICM is enriched. And this, of course, requires that the resolution, the spectral resolution of the spectrum is very high, of order of few EVs, in order to be able to measure this non-thermal broadening and the shift as well. And to do this, we had just one example so far that provided real, not upper limits, but real measurements of these velocities, which was Itomi, and did it for the center of the Perseus cluster. And we will have in the near future GRISM, which is a successor of Itomi, and possibly and hopefully Athena and Lynx later on to continue on this high resolution spectral path. All of these can actually be anticipated with simulations in a way that you use your simulated information and construct some mock X-ray data from which you can test the capabilities of this kind of instruments in reconstructing and measuring the velocity of the ICM. In particular, in this project, I will be focusing on galaxy cluster mergers in simulations, since our optimal targets to find very significant motions that can be more easily identified and measured, both in terms of bulk and turbulent velocities. And in principle, this is very useful, maybe not to constrain the non-thermal pressure support to the hydrostatic equilibrium, but so you probably wouldn't use such a case to reconstruct the mass via hydrostatic equilibrium assumption, but you can use the mapping of the velocity of the ICM in order to constrain better the geometry of the merger and to map the turbulence that you expect generated by this kind of events. So the simulations I'm using are controlled simulations of galaxy clusters, idealized clusters. We have several configurations in John's suite of simulation, depending on the input parameter of the merger or the mass ratio between the two clusters. And in this case here, I'm focusing on a non-radiative run performed with the Arepo code that includes dark matter and gas. And I'm going to describe a case for a specific and ideal study case where the mass ratio is 1 to 3 and the impact parameter is 0. So this is just a sequence of snapshots from the simulation. This is a temperature map of the system. This is the initial stage through the end. And here you have basically the first passage between the two clusters across each other. This is a y-x plane where the merger happens, and the maps are projected along the line of sight which is perpendicular to it, so the z-axis in the simulation. In particular, I will be describing results from this kind of, this snapshot here, which is roughly 1.6 giga-year after the beginning of the simulation, where you have a snapshot of the system soon after the first core passage. So with the shock produced here and the two cores that just pass each other, across each other. And we will investigate the velocity structure of the ICM in this kind of configuration, which is resembling more or less the Abel cluster I was showing before. The two clusters that are set up at the beginning with a 1 to 3 mass ratio are set up in a way that their profiles resemble cool core like clusters. So looking at the results a little bit from the simulation, these are again Z projected maps, so line of sight perpendicular to the merger plane at the snapshot I was telling you before. This is again the temperature map like before. This is X-ray flux estimated directly from the simulation, so no instrument convolved here. And this is a velocity dispersion map of the velocity dispersion along the line of sight, projected along the line of sight. And these pointings here are 7 pointings that we chose in order to map the system along essentially the axis of the merger and with 1 pointing off of it. The system is very symmetric, so what's interesting here is again to look at the center where you have the passage of the 2 cores. And as you can see, you have different regions in terms of velocity dispersion values, which can be very high like here, or quite modest, like in this case here, where you have some velocity dispersion of order of 100 or 200 kilometers per second. So looking into more detail about the pointings, we can start from the very faint one in the X-ray flux, which are interesting because they are located in interesting locations, regions. Here behind the shock and in front of it, along the axis and off of it, and in this region here where the velocity dispersion is very, very high, around 700 kilometers per second. And you can see that these are the velocity distribution along the line of sight in the different pointings, where the different lines with different colors refer to different weighting scheme. Once you deal with simulations, you have to choose the way you provide averages or numbers in general. And this is really crucial. As you can see, you can get, especially in this case, very different distributions. Black lines represent, let's say, the dynamical weight, in the sense that they are distribution weighted by the gas mass. So this is the true dynamical structure of the gas along the line of sight. The other lines, different colors, refer all to different kind of emissivity weighted distribution, which can be by using the Bremsstrahlung-like emission, or the emission associated to the iron line region purely, like in the blue line, or the emission measure. And all of them, you can see, have very similar features, so there is no big difference. And even in this case, all of them essentially smooth out the double peak in the distribution that you would expect from the symmetrical geometry of this case. So all of these pointings are actually capturing 2 components in the velocity structure that are very symmetric with respect to the line of sight, and that contribute to even very high velocity dispersion just given by the superposition of different motions. This is something interesting because it tells you that even if you are able to measure, not to resolve the specific shape of the line, but you're able to measure significant velocity dispersion, this doesn't really mean that this is turbulence or that this corresponds to a Gaussian shape of the line, since these are clearly not Gaussian. And in this case here, I will mention later, there is actually some third component at rest. This is line of sight velocity, which corresponds actually to a little bit of the cold core falling into my pointing. And again, these are the correspondence to the velocity dispersion. So if you look into the simulation, you can actually analyze in very detail the velocity and the thermal structure of the gas. This is again the velocity dispersion along the velocity distribution along the line of sight, and this is a phase diagram between temperature and line of sight velocity, color-coded by iron line emissivity, which allow us to understand the complexity actually of the thermodynamical state of the gas. And in this case, you can see that you have mostly one component, which is the hot one, that contributes to this kind of broadening. And if you translate this into an iron line shape expected by assuming simply a Gaussian as a toy model for the line, you see that in both cases, actually, the main features of the distribution are more or less preserved, although smoothed out. Here also thermal broadening is included, although minor. And in this case here is the one I was telling you before. This peak here corresponds to a different thermal phase of the gas, which is the cold core, whose photons, whose contribution is coming into the pointing I was using. So all this case, actually, all the pointing before, the faint ones, all show this double peak kind of symmetric distribution that you would like to measure as a non-Gaussianity of the line shape. If you look at more bright pointings in the center, where you expect some turbulence to be generated after the core passage, you actually find very different distribution. There is no more symmetry in the two components. You are not capturing almost anymore the shape of the shell of the shock that is expanding, and you have much more complex and broadened distribution. This one is very peaked in the center, but there are tails that actually contribute a lot. And you have very different broadening overall, even from the map, so from 100 kilometers per second to almost 400 or 500. So again, if you look at the distribution in the simulation, you see that the thermal phases can be quite complex, and this is something might complicate the reconstruction from the spectrum when you typically assume one single component. And again, the shape of the distribution is translated when you convolve with an expected line shape from the iron line. So convolving the single Gaussian with the velocity distribution, you get the theoretical line shape that you would expect. These all look kind of Gaussian, but they're not. So there are actually contributions that will distinguish them from Gaussian. So to do the next step and move to mock X-ray observations, we decided to adopt the specific characteristics of GRISM, which is the next in line among the different high-resolution missions, which is basically the successor of HEA and has a resolution, a spectral resolution with the resolve instrument that's quite high, between 5 and 7 AeVs over the quite wide energy band, whose field of view is 3 by 3 arc-minutes squared, which correspond basically to the pointings I was showing before, that are 200 kiloparsec side in size, in physical size, and correspond to this field of view once you put your cluster at a redshift of about 0.06. So GRISM, HEA actually already proved to be able, as I was saying, to measure velocity shift and velocity dispersion for the gas. This was done for the core of Perseus, so very bright region of a nearby cluster. And GRISM is supposed to extend this kind of work and look at a greater sample of clusters, mainly cool cores for the bright central parts. And in principle, you can use it to evaluate the impact of mergers, as we are doing with the simulation study, in order to map the different regions of possibly close-by clusters, to map the velocity structure in merging systems. So what we do with simulations, we generate mock X-ray data, assuming from the simulation that each gas element in the simulation does emit as a single temperature APEC model. We then combine all the photons expected from all the different gas elements in the simulation by using the PyXim algorithm. And then we produce 100 kilosecond mock observations for GRISM and analyze them. So we produce actually one observation per pointing for all the 7 pointings I was talking about before. Once we have the mock images, we can extract spectra, and we can then fit them in the region comprising the iron line complex at 6.7 keVs, more or less. And to do this, we use a broadened APEC model in order to account for some non-thermal broadening of the line, in order to estimate line shift and broadening. The main and first goal of this exercise is to actually assess the reliability of the reconstruction from the mock instrument once you know the true distribution from the simulation. So about the faint regions, unfortunately, this is the theoretical X-ray flux map, and you see already by eye that they are one order of more of magnitude fainter than the bright part in the center. So we did try, of course, 100 kilosecond exposure is definitely not enough in this case, 500 kilosecond exposure, not even. We tried to increase up to 1 or even 2 megaseconds just for exercise, and of course this is not something realistic, so I will just move on and show the images, which you can see again by eye. The number counts is too low, especially it's too low in the 6 to 7 kV band where you want to fit the line, and you have to have enough statistics in order to constrain something reasonable. We did even try to exclude the bright part here just to catch the region in the shock by assuming a super high spatial resolution and cutting out the part including the core, again, even worse than before. So let's move to brighter things. We consider these pointings in the center. These are the much brighter images obtained 100 kilosecond exposure for Grism. These are the spectra in the 6 to 7 kV band and the best fit model. Down here, I'm plotting the numbers that you want to compare to the simulation. So when you have the simulation, a tricky point is to get out numbers that are actually comparable to X-ray data, or to mock in this case. The first thing you can do, of course, is to calculate averages, weighted averages, and velocity dispersion just from the distribution of the gas, and you get a theoretical estimate, which not necessarily resemble what you get from XPack, which is in fact more similar to a single one Gaussian fit of the distribution, since this is the model assumed in the broadened APEC one. So just to compare the results from the fit with respect to the simulation, you can, first of all, use different weighting schemes, again, from the simulations, but this doesn't change too much between emission measure and iron line emissivity. And I would say that for the best pointings, we have more or less all of the XPack reconstructions are consistent with the expectations within 1 sigma, or slightly more in a few cases. Differences are also very interesting, however, because it doesn't really necessarily mean that the fit is not good. It rather means that the fit you're performing is not catching the complexity of the distribution of the velocity in this case. Again, because you're fitting with a single Gaussian and you are actually using some velocity resolution from the spectrum, which is high but not as high as the one I'm showing here. So one thing you could do is to degrade the resolution of the velocity distribution and just fit with a single Gaussian. And in this case, you might get something more similar to what you expect from the fit. Also, a caveat I want to mention is that with this kind of procedure, every time you generate a mock, you actually get one possible realization of due to Poisson noise from the system. And in principle, you want to do many more just to constrain the best fit values and be sure that they are consistent with what you would expect. Just very briefly, the other extreme is to use the X projection, so along the line of sight, and consider one single pointing in the center. So the region is super bright and you expect to detect very significant motions just because it is along the line where the two cores are passing each other. This is just the very first results. Here the distribution is much different. There are two peaks, but they are clearly not symmetrical, so they are actually corresponding to the gas associated to the two clusters. And the center shifts are very significant, so you would expect large motions to be detected. Even if you convolve with the line, of course, these features are preserved. And in the phase diagram, you see that the two components are clearly distinguished and both very bright, also in the temperature range. So this is the whole pointing image. This is, again, the spectrum with the best fit. And in this case, of course, you wouldn't like to fit with a single BAPEC model because you know already and you expect to have in this case, two different components, both in temperature and normalization and velocity values. So in this case, you would use two to identify the two velocity structures, and results again are consistent with what we expect. So the biases you can constrain are due to projection or weighting scheme, like in the one of the faint regions before, and you can use this kind of study to again not only predict what you are able to do, but also constrain a little bit the biases you expect to have in the pure reconstruction, but also in what you can actually measure about the intrinsic structure and what you cannot, because you are simply related, confined, let's say, by the X-ray observability of it. And yes, these are more or less my conclusions.
Very nice bringing together of the theory and the observations. You emphasized at the beginning that what we see with the X-ray gas is sort of determined by the dark matter distribution. So I was wondering if you could please say a few words about what you assumed about the initial dark matter distributions and how you might, how the simulations might give somewhat different results if you altered that.
So what I meant is just actually that the gas fills the potential well, and therefore it reflects its depth. This was the basic concept behind that. In this case, the two dark matter halos of the clusters are Navarro-Franken-White profiles, and these are set up again together with the other profiles as initial conditions for the two clusters. So of course, if you have different conditions, you might expect different features in the ICM, but in principle, this is done mainly by the merging process. So what I am investigating here is the result on the gas structure due to the merging event between the two clusters.
Right, but if you did have a different dark matter distribution to begin with, it looks as if possibly your simulations would give some guidelines to be able to learn that.
Could be, yes.
So in that sense, it seems like you have very powerful methods.
Yes, yes. I mean, with simulations, yes, you can start with many different conditions in terms of dark matter and not only, and explore what you would expect, or if you could expect measurable differences in the results. Yes.
So the data she's working with, we have simulations that also include self-interacting dark matter, which causes the potential to change. So that's further down the line. This is a really good start. So.
And secondly, is it correct to interpret your last plots as suggesting that if you have spectra, so if you can measure the velocity structures of galaxy clusters with something like Prism or HEA or whatever, that you would be able to catch line of sight pointers, which would be done?
In principle, I mean, here let's put it like this. In this case, I tried to see whether it was possible to reconstruct something that I know is there. If you have like an image like this, probably by eye, it looks really roundish, and you wouldn't think about a merger along the line of sight unless you're very lucky and you catch it. If you do, you would be probably able to tell this, because with very high spectral resolution, if the motions are high enough to produce a significant shifts, different shifts in the line, from the shape of the line, you would be able to reconstruct the double peak. But again, this is still an ideal step. So
from moving from Prism to Athena to lens, improving your vector resolution from 4.5 EV to 2.5, and lens is
3 something.
But how would that help you in terms of the
So this would probably get things worse because it's really difficult to, no, I'm kidding. It's really difficult to properly fit these things with such high resolution. But yes, it will, of course, improve because you can resolve better the motions and the features of the line. Plus, like for instance, if you mention Athena, you have like much larger collecting area, so you would be able to get this kind of study also to the fainter regions.
All right, as I mentioned, she's here all summer, so let's thank Veronica again. And our next speaker is Elizabeth Blanton, and she's going to be moving us from simulations of galaxy clusters to observations of galaxy clusters. She's an associate professor at Boston University. She got her PhD at Columbia, and her thesis was on event double radio sources, which is part of what she'll be telling us about today. She was then a postdoc at Carnegie Mellon and then University of Virginia, where for some time she was a professor. Her research interests are in galaxy clusters, the physics of the ICM, AGN feedback, and looking at all these things in a multi-wavelength X-ray, radio, optical IR. And today she's going to be telling us about the Quasar survey, which is high redshift clusters occupied by bent radio AGN.
Maybe. Just need to balance this.
If there's actually, it's not reaching, there's actually
It's reaching, it's just trying to get this right. It's going to be fine. Okay.
There we go.
Oh, okay. Is there a pointer? Yes, there's a pointer. Okay. Yes. Got it. Okay, thanks. Okay. This, yes, on? Am I on? No. Okay.
It shouldn't have been turned on.
Oh.
Oh, it was the other one?
I don't know, it was the one on top.
Okay.
I don't know which one you took.
Yes, this one's
I'm going to get there. Okay. Yes. Now? Yes? Okay, great. All right, so this is going to be a very multi-wavelength discussion of a survey that we've been undertaking for a few years called the Cobra Survey, and I'll give you an overview of the development of the survey over the years and where we are currently. So it's the Cobra Survey, which is not too contrived of a name. I was sitting at a conference a few years ago and I realized everyone had a name for their survey, so I came up with this name, Clusters Occupied by Bent Radio AGN. And it started off, we were doing work on these kinds of clusters looking at lower redshifts, and so I'm going to be focusing on the progression from that into the higher redshift realm. So this is a Spitzer infrared image shown here with radio contours of a bent radio AGN superposed. So you can see the host galaxy right in the middle there, and then you can see the extended jets and lobes coming out into this characteristic C shape here. So the idea for the formation of these sources is that they're embedded in a cluster in a dense ICM, and so that there's some relative motion between that gas and the radio jets and lobes that results in them bending. So it's sort of like hair blowing in your wind, something like that. You can get that from just the galaxy having a significant peculiar motion throughout the cluster, or you can get it in large-scale cluster-cluster merger where the ICM is set into motion and just blowing back basically the jets and lobes. So that's the conical idea for the formation of these things, is that maybe they're in cluster mergers frequently because they're typically associated with dominant luminous elliptical galaxies in clusters. So CD galaxies often right at the center of the potential well. that you don't expect to have a really large peculiar velocity. So something has to still bend the lobes. But anyway, if we can look at radio surveys and we see these types of radio sources, we say, aha, okay, that's probably located in a cluster or maybe a group, something. There's some sort of extended medium around that radio source that's causing it to bend. So that's the idea behind the survey, is to assemble a bunch of these types of radio sources. They're selected by morphology, and then do follow-up observations to find clusters. So something like the VLA first survey, which we used at 1.4 gigahertz, you can see these sources quite easily to Redshift 2, 3 on just really short snapshot observations, where obviously you're not going to easily see a cluster in an X-ray survey or an optical survey that easily. Okay, so here are my collaborators over the years on the project. The people highlighted were all my PhD students at BU, current or former. Actually, this is from the first to most recent. So Ned Douglas, Josh Wing, who's currently here, Rachel Paterno-Mahler, and Emmett Golden-Marks, who I know some of you may have heard some results from recently on the optical component. Okay, so in general, we know that radio sources associated with AGN in general, not just bent ones, are in clusters at a range of redshifts, low redshifts, high redshifts. They're very important to the evolution of galaxies and clusters as a whole. They provide feedback into their host galaxies and the intercluster medium. And certain types of radio sources can be used, as I was talking about, as beacons for finding new distant clusters that are very difficult to find otherwise. Okay. So these potentially give us a sample of clusters that are selected in different ways than other common survey techniques, so different than what we might see in the X-ray or optical or SZ. So we'll find that these clusters have a wide range of masses, so a lot of surveys will just select preferentially the most massive clusters. These are going to select a wider range of masses. They may select clusters that have some interesting dynamical activity going on in them. And of course, by the nature of their selection, they're clusters where we expect there to be AGN feedback because they have these big extended AGN in their cores. We found that these bent sources, which are basically wide-angle tail type sources, they're not necessarily officially wide-angle tail in the details, but basically wide-angle tail type sources are efficient and more efficient when you compare it to straight lobe sources or single component sources. So we can go out again to very distant redshifts with this. Okay. So what we have found is that this is the type of source we're looking at. They classically are more often in clusters than in FR2. So an FR2 source classically would be collinear, would have edge brightened lobes, would have a higher radio power. Then an FR1 would have edge dimmed lobes, often distorted. And then this is an FR1, Fanneroff-Riley class 1, wide-angle tail or bent-like source in particular. Okay, so this is kind of the classic idea of what the environment of this type of source would look like. This is from Ned Douglas a few years ago, 2011. This is Abel 562. On the left is an optical image, and you have X-ray contours on top from Chandra. This is the Chandra smoothed image here. So you can see there's actually two luminous CD-type galaxies in the core. Looks classically like a cluster-cluster merger along this axis, and you see this large radio source. So the idea is that you have some bending of the lobes because there's a flow of the gas in this direction. Okay, so there's sometimes in kind of environment, but they're also found in environments that are thought of as classically very relaxed, cool core clusters. So this is Abel 2029. This is an early image with Chandra showing that it looks quite smooth, symmetric. This is an optical image to the same scale. And this is if you subtract off a model of the smooth emission and you bring out residuals, you can see a sloshing spiral feature in this particular cluster. We saw this early on in 2004. This was a pretty early example of a sloshing spiral, and if you zoom in and look at the center region, you see this little radio source that's bent, and you see that the sloshing gas looks like it's running right into that lobe and bending it. So you see sloshing features like this in clusters that are not very disturbed. They're supposed to be relaxed, cool core clusters. Okay, so we can find these types of radio sources, not necessarily in big, large-scale major mergers. They can be in pretty relaxed clusters too. And then this is more recent data, deeper observation of this same cluster where you can see the same thing, but you just see this beautiful spiral extending out farther, and then the interaction again in the core with the radio lobe. And that's from Rachel Paterno-Mahler. Oh, the other thing that we can do is that we can constrain the velocities of the ICM. So in combination of using some information from the gas, the density and pressure in the environment of the radio source, making some assumptions about the content of the radio source, the jets and lobes, we can arrive at an estimate, a sort of an indirect estimate of the velocities within the ICM. And so we get something in this system, something like 150 to 300 kilometers per second for the flow in this sloshing spiral. And that's sufficient to bend the lobe. So you don't need a really large scale merger with a velocity of 1,000 kilometers per second in order to get that bending necessarily. And this is consistent with the numbers that you get when you look at simulations of sloshing and interaction with these sources. Okay, so one thing that we did when we were starting this project was to look in the archive of Chandra and look at the X-ray environments. Okay, so this was a sample. This was Ned Douglas's dissertation, looking at this sample of 12 systems that all have bent sources in them and trying to see what kind of environments are they in typically. Are we always going to find mergers, or most often going to find mergers? We're always going to find sloshing. If we're looking at these really high redshift clusters in our survey, what are we getting ourselves into? What kind of systems will we find? So that was the point of that work. And so he came up with these different criteria to characterize a cluster as being more of a cool core cluster or a merger. So these are the cluster names, and then this is just saying, temperature profile, does it drop in the middle? If temperature drops in the middle, it gets a 1. Something like, does it show a sloshing spiral? Does the cooling time what you would expect for a cool core cluster? So all these things add up. So as you would expect for cool core clusters that have already been classified as cool core, they get a large number here in their total cool core characteristics. If you then take a comparison sample of non-cool core clusters, so these are not ones with wide angle tail or bent double radio sources, these are just comparisons. So the non-cool cores, they don't have those features, okay, by definition. So if you look at our sample of the wide angle tail or bent doubles radio source sample, you see sort of a mix, okay? So you see things that look like a cool core, they have a lot of these features, something like that one or this one. And then you see other ones that look more like non-cool cores. So basically what this is telling us is that our survey will uncover a mix. We'll see some large-scale mergers, we'll see some cool core clusters. We're not just getting one type of thing. Okay, and then another step in the process was to then look at the low redshift environments in the optical. So this is work by Josh Wing. And so the correlation here was done with sources from the VLA first survey and the radio with the Sloan Digital Sky Survey. So I originally started some of this work back when I was in graduate school and Sloan didn't exist. So I had to go out one by one and observe each field. And I think, I had a sample of 40. But he was able to do hundreds, thousands of them actually, and define different samples in the radio. So we looked at bent sources, a comparison sample of straight sources in the radio, and then single component radio sources. And so there's some details of what these different samples are, ones that were bent that were selected by eye, ones that are bent that are selected by an algorithm, straight ones, single component ones. So cross-correlate those radio samples with the Sloan survey and see what we get. So first of all, of course, you're going to be limited in redshift because Sloan is limited in depth. So we're going to basically be able to recognize host galaxies out to about 0.7. We can really sort of measure a cluster, so the host and surrounding galaxies out to about 0.5, doing that work. We can further break down sources that are more quasar-like versus just elliptical galaxy-like. So this is color, magnitude of R minus I versus redshift. So the quasar objects are going to be bluer. The elliptical galaxy-dominated objects are going to be redder. So in this work, we just drew a line here and looked at the environments of the radio galaxies, the elliptical galaxy hosts, and didn't go into the environments of the quasars in this work. And for the most part, in the Sloan survey, we wouldn't be able to probe out here anyway because it's not deep enough. We can also separate into the classes I was talking about earlier, Van Ralph and Riley 1 and 2. You can do that by eye, morphologically. You can also do it by, there's this relationship between radio power and absolute V magnitude, where you have a correlation between those two things, and you can draw a line that's separating the FR2s up here and the FR2s up here and the FR1s down here. Okay, so these are some examples from that work. These are all from the first survey. This would be like a bent FR1 radio source, a bent FR2, so it's brightened at the edges. This is a straight FR2, a straight FR1. Okay. And then Josh went through and measured the environments or surrounding the radio sources. So this is saying there's an excess number of sources around the radio source, some number greater than 40 galaxies in the environment of the radio source. This would be still an excess, but only 20 or more. Basically, you can just look at this column to see the differences. So these are our bent sources. These are the straight sources. These are the single component sources. So basically what you see is that the bent sources are more often in dense environments. Okay, so this was really nice that we could do this direct comparison. Are we doing any better with a bent source versus just any other kind of radio source? Because we know all different kinds of radio sources live in clusters, not only bent ones. So are we actually going to do better if we start with these? And it seems like, yes, we are. And this is breaking it down into FR1 and FR2, same thing. But basically, the FR1s are more in clusters than the FR2s, as we would expect. Okay, and this then is an example of a lower redshift cluster. This is at redshift 0.25 from the Sloan Digital Sky Survey. Here's the radio contours. I'm zoomed in here, and then here's the cluster there. Okay, so through that work, we identified a large number of systems that did not have hosts in the Sloan Digital Sky Survey. So here are some examples. Here's a radio contours overlaid onto an optical image from Sloan, and you don't see anything there. Okay, you don't see a host. You don't see a host. Here you do. This is actually a quasar. I think this one's at 1.8, or maybe it's that one. But anyway, you get the idea that we can then pick out cluster candidates by saying they're not detected in Sloan. There's got to be something there. So those are our high redshift candidates. So let's follow those up in the infrared, in the optical, eventually the X-ray. Infrared is an efficient way to go. If you look at magnitude versus redshift, this is 4.5 micron. So you can see how it kind of plateaus as you continue with a redshift. So there's some dimming, obviously, as the galaxy goes to higher redshift, but then you're also shifting the peak of the emission more into the band that you're observing. So if you observe at 4.5 or 3.6, it's an efficient way to go. If you try to do B band, obviously that's not a good way to go because it just gets too faint. Okay, so we had a snapshot program with Spitzer to observe 653 of these sources that were like that, so they weren't detected in Sloan. They're nice bent double radio sources. Almost all of them got observed, 646 of them. Most of them were more like radio galaxies. About 40 were known quasars. And through this work, we found 200 new clusters and groups with, this should be actually redshifts above more like 0.5. All were observed in 3.6 micron, and then a subset in both 3.6 and 4.5. Ooh, okay, so Cobra. Wow, that's flashy. So this is C-like, right? Okay, clusters occupied by bent radio AGN. Here we go. You could really call the whole survey Cobra, but we didn't adopt that name until we started doing the high Z work. Okay, so the high Z Cobra survey ranged 0.5 to 3, wide range of masses, groups to clusters. Again, by the nature of their selection, they all have AGN, so we can potentially look at AGN feedback at this wide range of redshifts. You're generating a sample to look at galaxy evolution over time in group and cluster environments. Maybe sometimes they're tracing out large-scale filaments, because sometimes you can get the bending from infalling gas along a filament and clusters in formation. So with our Spitzer observations, we can get an overdensity in terms of the galaxies there, and we can get an idea that there's a cluster there. Don't really get much of an idea of redshift unless we have a couple bands there. So we also then added on a bunch of optical observations. So we've been doing work there, and this is work that Emmett Goldenmarks is doing using the Discovery Channel telescope, which many of you, well, maybe you've heard me mention it before. It's a pretty new telescope. I think it had first light around 2012, 2013, something like that. It's a 4.3 meter optical telescope out in Happy Jack, Arizona. It's got this really nice large GCD, the LMI, 12.3 by 12.3 arc minutes. So we've used made extensive use of that and observed about 100 of our cluster candidates. Okay, so if you have, this is just showing you that if you have I band and 3.6, so you can get a nice color, that is very strongly correlated with redshift. And so you can get a redshift estimate there if you get those multi-bands. So here we're going back to our candidate fields and then some of the discoveries we've made of these high redshift systems. So this would be one in the R band, looking at the environment of this radio source. You're not seeing much there. Spitzer, you see a really obvious cluster just pop right out. And then this is the nice image in the I band. Sometimes we get great seeing there. It could be 0.6 arc seconds. Sometimes it's 3. So it highly varies. This is another one. We have a redshift estimate of this of 1.1. So you can see it here. It's got this unfortunate foreground star, which makes it a little challenging. This one, which is the poster child, because it's such a nice C, and this is not very good observing conditions, but you can see that the host is detected there in the I band. And then this one is a Quasar Environment, and there's all kinds of stuff going on here in Spitzer in the 3.6 micron image, but it is significantly detected there. Okay, so some of you have seen this image before. This is a highly smooth Chandra image of one of these fields, but it is there significantly. So you can see that this was just a 20 kilosecond observation pretty early on with Chandra, so it is detected. This is a field where we have spectra for 10 of the galaxies with Keck, so I don't know if you can really tell, but the ones that have the thicker circles, the yellow there, those are the ones that are spectroscopically confirmed, and then the ones with little lines. So there's 10 that we have spectra for. The other ones are cluster members based on color. So we can measure a velocity dispersion. We can get an X-ray luminosity, which is about what we expect based on the optical observations. Okay, so this is a sort of a couple times 10 to the 44 ergs per second system. So looking more at the Spitzer observations and how we determine cluster candidates there, this is from the dissertation of Rachel Paterno-Mahler. So what she did here, there are 2 histograms here. So the black is showing us the percent of fields that have some number of galaxies within an arc minute. So looking at our whole COBRA survey, 646 fields, how many have, 40 galaxies within an arc minute, how many have 60. So you get this black histogram. If you just do some background survey field like SPUDS here, that's the red dashed histogram, okay? So you can see that our distribution has shifted a bit to the right. So on average, our fields have more galaxies around them than just a random field. So what she did here was draw this vertical line here to say everything to the right of that line. These here are the cluster candidates. They have an excess of galaxies within an arc minute compared to what you would just get randomly. Okay, so that's saying it's not like all of our fields are really rich clusters. You can see that there. Here's another way of looking at it. It's looking at the number of sources within a 1 arc minute radius or the number of sources within a 2 arc minute radius. Okay, so something above 0 or above 0 this way, that's a positive number of galaxies. So most of them have a positive above the background. This would be a line showing the more significant couple sigma level. This is a more recent Redshift distribution. So this is combining the optical and infrared data here and showing now that we're going out to a redshift of almost 3. So this is only for cluster candidates and only for ones where we have redshift estimates. So it's only about 150 of the sources here. So you can see that there still are a lot at around a redshift of 0.5 that we're starting to populate these higher redshifts. And the black is the distribution when you combine the optical and infrared. The red is what we just got from just the infrared. So when we have the multicolor information, we can start to fill out this region a little more. Okay, so of course we want to observe these in the X-ray. So we have a couple things going on there. We have a Chandra Cool Target CCT program that was approved. None of them have been observed yet, so we're just crossing our fingers for that. But 102 of those are on the list. We limited it to redshift between 0.5 and 1.8 because we wanted it to be high enough to be interesting, but not so high that we would never detect it within the exposure limit of a CCT program. And then 3 of our best candidates were recently observed with XMMNewton in a pretty narrow redshift range, 1.1 to 1.3. All were very significantly detected, actually better than I was expecting. And I'm going to show you luminosities. I don't have a lot of information on those. These contours you might think are X-ray, they are not. So this actually is an I-band image. There's a radio source here. These contours are just surface density with the I-band galaxies. This is if you do a color cut, so we really can localize the cluster a lot better and eliminate foreground objects if we only look at the galaxies that have the right color to be at the redshift of the host. So this is these are surface density contours based on I minus 3.6 color. This would be the black line is centered on the radio source, and the cyan line, circle is centered on the peak of the distribution. This is detected with XMMNewton, 6 sigma, about 3 times 10 to the 44 ergs per second. So same situation here. You can see the radio source here. It's kind of offset from the peak of the distribution. And then this is even a stronger detection, 8 sigma with XMMNewton, about 6 times 10 to the 44. And all of these were only about 20 kilosecond observations with XMM. And then this one, it's maybe about 10 to the 45 ergs per second, 16 sigma. So that was really strongly detected, about 750 counts in something like 20 kiloseconds. And this is a redshift 1.2. So those are all similar redshifts. So that's ongoing work. I'll be working on that this summer to get more information on the XMM observations for those fields. The goal there was pretty much just to get the luminosity and then go back and reapply with Chandra to be able to make sure that we're cleanly separating any point source from extended emission. Okay, so I'll wrap it up. So I talked to you about history and ongoing story of the COBRA survey and where we are now. So it's a nice cluster finding technique that's different from other methods, complementary to other methods, going to find a wide range of masses, sometimes dynamically interesting systems in which we can study AGN feedback for sure. And so far, our X-ray observations are really encouraging, that they're really confirming that these are bona fide clusters. So I'm hopeful about the future there. Okay.
So how many of these have been seen working finally?
We've looked at that, not a lot. I don't remember the number. I know we looked. Not a lot. They're not, I mean, they're, so the first survey is, 10,000 square degrees. And we have maybe, 1,000 of these sources over that size. So they're not really common on the sky.
So, focusing on these special bent ones
Yeah.
gives you a very nice way of finding clusters.
Yeah.
For every one that you find this way,
Yeah.
can you do some population statistics saying, well, this is the number I find with we therefore know there must be some larger number totally?
That is something we've thought about. It's pretty tricky because radio sources are evolving with Redshift too. And so trying to, because we can study them very well in detail at low Redshift and we can see those kinds of ratios, but then to apply that to high Redshift, I'm nervous about. It's not an easy thing to do because...
Have you been able to see that there's redshift evolution over the nearby ones where you have some range in redshift, but they're still relatively nearby?
That's something that we want to look into more. To look at things like, does the richness of the cluster evolve with Redshift? Just all those kinds of things that you would obviously look at. We don't see a lot of whopping trends yet, but that's something that's still ongoing that we want to look at, yeah.
Any final question? All right, let's thank Liz.
Okay, thanks.
Very nice.
Thank you. Yeah, it's tricky. It's something that we would like to be, and also the really cool thing, because with all the new radio surveys coming up too, to just be able to say, just skip all the follow-up, just look at the radio sources themselves, and and if we just assume that those are all in clusters, what is that? Just make those kind of measurements just based on the radio alone. You could kind of do that. It's tricky.
Yeah, of course you have to be careful.
Yeah.
It's interesting because I've been looking with Dan DeRazio at self-lensing when you have a merger, right?
Mm-hmm.
And I think this is very interesting because at X-ray wavelengths you could see this. And we even have a candidate that we're investigating right now.
Uh-huh.
So it might be interesting to talk about this a little bit since you're going to be getting these longer I hope you're going to be getting these longer X-ray observations.
Yeah.
It would be interesting to see what can be done with it.
Yeah, for
Since
sure.
some of your systems are mergers, not all
Right.
of them, but since
Yeah.
some of them are,
Yeah.
the question is, do any of them still have the double, black hole or
Right.
are they all merged?
Right.
With the double black hole at the right stage in its life, you could potentially
Right.
measure the masses.
And sometimes, those types of radio sources, it could be from that. Sometimes it's hard to tell. Is it just a single source that's measured? It could be because the resolution is not great, so you could get a kind of, one jet's coming out like this or something, so it looks like a vent source.
That's what I was wondering, actually.
Yeah.
Well, it would be great. I think a lot of people want to talk about it. So maybe we can follow up another time.
Yeah,
But
that sounds
anyway, I was
good.
really pleased to see you.
Great, thanks.
I just wanted to
Hi.
say hi.
Hi.
See how you were doing. I really enjoyed the talk.
Thanks.
I also thought this was a very cool program. Ever since talking with Josh about it when he first came, I thought, my gosh, yes, this is a great way to do things.
Yeah.
And as Josh was saying, there are so many possible spin-offs from it.
Right.
And,
yeah, it's like this never-ending
And
story.
well, that's what you want.
It
You
just
want a
keeps
major program that gives you
Yeah.
these endless rewards.
Right.
So
Yeah, because
Yeah.
there's some things that we haven't, looking at the ones that are in poor environments, which we keep talking about doing, but maybe those are filaments, maybe those are fossil groups. They're interesting things that we
These
haven't
things may
really
even
done.
be a bit more common than you think because you only see the ones
Oh.
that are
That's embarrassing.
in sideways projection. And there are
Right.
the curved ones that you see edge on. And of course, you'll never know that. But,
Right.
um,
Yeah.
Test, test. Jesus, can you hear me back there?
Are you presenting?
Yes.
Would you like to try just to make sure?
Why not?
Can't hurt.
It's always a good idea to check, isn't it?
I can turn those lights off up there for you. That was part of the last group.
Sure.
Upstairs. That should come on. Yeah.
Looks good.
Any sound or anything like that?
No.
Great. Nice and easy.
Be straightforward. Very good.